So I'll give you a few insights into what we are doing in the group. Mostly we're working on molecular sciences, of course, and we are now interested mostly in developing machine learning and AI methods in order to make progress on some of the basic questions in molecular science and some of the technical challenges, I should say. And generally, when developing machine learning or AI methods, one basically is confronted with two questions, namely, what is the optimization problem and what is the learning structure like? So because machine learning problems are usually phrased as optimization problems, and on the other hand, learning structure, that means what is the neural network structure or kernel machine or whatever data structure which holds the parameters. And when we're dealing with physics or physical chemistry, then fortunately, the physics can tell us a lot about these choices. So for example, the optimization problem could be as simple as just a supervised learning problem where we have labels given that we're trying to match. That's probably the most common use of machine learning. But in physics, very often we have more fundamental things going on. For example, we may just have like a variational problem that tells us that we want to variationally optimize some quantity. And in the limit of doing that, we'll solve an equation or solve another problem. And then we can use that as our optimization problem or our loss function. And likewise with the learning structure in physics, we often have certain expectations on the solution of a problem. For example, we would like, if we learn or if we predict an energy for a molecule in implicit solvent or water, or a bulk water, then we expect that to be invariant to translation and rotation. And such constraints can be built into the neural network right away so that we don't have to learn them. And well, in some cases, it can be quite tricky how to do that in practice. And then that means one has to essentially think about how to design the neural network such that it automatically satisfies these constraints and is still expressive enough that we can learn the maybe complex function to solve the problem at hand. Now, in that spirit, we're working on several applications of machine learning to the molecular sciences. As Rebecca already said, we've been working a lot on molecular kinetics after I set up my group in Berlin. So especially working on things like Markov state models, and there are also now deep learning versions of Markov state models where based on a variational formulation that we have developed, the deep neural network is trained to find an optimal transformation of the molecular coordinates into collective variables that determine the slow processes, so the rare events in the system, and then basically learn a Markov state model in that space it has learned. And that's interesting because I mean, previously Markov state modeling has been a very cumbersome manual process of essentially designing a pipeline that goes from the molecular simulation data through several steps of dimension reduction and clustering and transition matrix estimation and coarse-graining that transition matrix, etc., etc. And now with this formulation, you can basically just do it with a deep network which replaces that pipeline and learns it end to end. Then we're working quite a bit on coarse-graining now. So we're very interested in developing coarse-grained force fields, especially for proteins, with the help of machine learning. So I'll talk a little bit about that. We're very interested in the sampling problems, or always have been, because I think sampling always has been and still is one of the main bottlenecks in molecular simulation, at least if you're trying to simulate like non-trivial molecules, and then also on electronic structure as well. So I'll start off actually with electronic structure. I know many people in the audience are maybe interested in the classical simulation side as well, but I've definitely seen a couple of people that might be interested in electronic structure. And so basically, when you're thinking about machine learning for electronic structure problems, probably the first thing that comes into mind is that one can do supervised learning on pre-computed quantum chemistry solutions for small molecules. And many people have done this extremely successfully, and there are several of the pioneers here in this picture. And basically, the state of the art there is such that, at least for small molecules within a class of compounds, let's say organic compounds, we can essentially be so accurate with our predictions that the bottleneck is not the machine learning prediction, but rather still the intrinsic error of the quantum chemistry theory level. But then, of course, the question becomes, can we maybe generate better baselines and it's like better solutions for these molecules, so that we can train the next level of supervised learning methods that make predictions across chemical space. And so essentially what we want to do there is we want to solve the Schrödinger equation to a very high accuracy. But now we want to use machine learning methods to do this. And so let's look at the Schrödinger equation. This is the stationary Schrödinger equation, time independent, non-relativistic, and I'm only going to look at the ground state here. And basically what we have here is we have to solve an eigenvalue problem. So we have a Hamilton operator which determines what system we have. So which electrons and protons are interacting in our molecule. And we're looking for the wave functions, so the eigenfunctions of this eigenvalue problem and the energies, which are the eigenvalues. And for now, as I said, just the ground state. So generally, quantum chemistry is kind of a trade-off between higher accuracy and higher computational cost, with DFT being one of the famous outliers here, because it can give quite high accuracy if you choose the right functionals at quite acceptable computational cost. And we believe that we can also create another outlier here, which is basically at a higher accuracy but higher cost level as well. And that is quantum Monte Carlo, which leverages deep learning. And so the basic idea here is we formulate the solution of the Schrödinger equation as a variational approach. So we minimize the variational energy, which is given by this integral here in the top right. And then we can represent our wave function with a neural network, and our loss function becomes the variational energy. Now, of course, we cannot solve this integral analytically for arbitrary functions, and therefore we turn this into a quantum Monte Carlo framework. So we basically sample the integral with Monte Carlo. So the electrons really become samples that are like pseudo particles that are diffusing around the atoms. And they're being sampled from the square of the wave function, which is given by what our neural network currently represents. And then we compute the average of this so-called local energy, which can be easily computed when we have a function that for psi that we can evaluate. Okay, so main problem here is that electronic wave functions are antisymmetric because electrons are fermions. So we have to respect the fact that if we exchange two electrons, we have to change the wave function, the sign of the wave function. And that leads to these nodes in the wave function, which leads again to Pauli exclusion of same spin electrons. And that's what makes the problem hard, basically. So we're introducing a combinatorial argument. So solving the electronic Schrödinger equation exactly becomes basically exponentially hard in the number of electrons because of this. But of course, we can try to make the problem not exponentially hard for a set of problems that we are interested to solve with a given method. And so the key idea here is to use, as common in quantum chemistry, matrix determinants, Slater determinants, to represent antisymmetry. So that basically means we write some entries into a matrix and use the fact that by exchanging two rows of a matrix, the sign of the determinant changes. So we use the determinant basically as a building block for our wave function. Now, in classical quantum chemistry methods, in classical wave function methods, the idea is to take functions from a basis set, and then assign electrons to these functions and write the pairwise evaluation into the Slater matrix and compute its determinant. Now, if you don't change, if you fix the functions, then this generally means that in order to get a solution for a given molecule, you're not getting a very high accuracy result with a single determinant or a few determinants. If you want to get a high accuracy result, you need to use many determinants. And these many determinants come from the fact that you can select many subsets of n functions from a larger basis set. So that's the fundamentally combinatorial problem here. And the neural network idea is now to thread the electrons through a neural network and say, well, we input them into a neural network. This neural network has some properties that need to be respected. For example, it needs to be permutation equivariant. That means if we exchange electrons at the input, the outputs have to exchange as well. And but what this neural network does, it does a nonlinear coupling of the electrons with each other, and the resulting particles at the output of the neural network, these pseudo particles or pseudo electrons, have no multibody information in them. So if you insert them into fixed functions, then effectively that's the same like learning to change the function. And then the hope is that you can get away with many less matrix determinants at a given, to reach a given accuracy. So the overall learning system looks like this. Basically, the orange stuff here are neural networks. The top right is basically a block which is represented by a graph neural network, where the nodes of the graph are the nuclei and the electrons that are interacting with each other in a particular way. And all the green stuff basically is physics. So basically that's including physics of wave functions, making sure that wave functions have the right asymptotics as electrons approach other electrons or nuclei. Or we make sure that the baseline that we start with is at least a Hartree-Fock solution or the CAS-SCF solution for multiple determinants, so that we basically only learn the correlation energy with our neural network. And so by training this like a Monte Carlo, a quantum Monte Carlo framework using this neural network on a given Hamiltonian, we can essentially approximate the solution of the Schrödinger equation. And here you see for small systems that we can approach very high accuracy solutions that can otherwise be obtained with standard quantum Monte Carlo method, with a factor 100 less matrix determinants than standard variational Monte Carlo, and with comparable accuracy as diffusion Monte Carlo. And we can also go to more complex electronic systems, such as this here, cyclobutadiene. That's still a small system, but it's very challenging for quantum chemistry methods. So you need specialized multi-reference coupled cluster methods, which scale as n to the 7 and need some choices to be made that are specific for this system in order to reach experimental accuracy here. And basically we can get there with this Paulinette approach by just training on this Hamiltonian with a method that is formally n to the 4. In practice, we observe n to the 3 so far for the systems we've run so far. And the method is black box. So basically, this is exactly the same neural network that we used for the single or diatomic molecules. So, and currently we are extending this framework in various directions. So we're working on excited states as well, on transferable and a transferable network that can essentially variationally optimize entire potential energy surfaces, and on various applications, especially to systems that have kind of non-standard Hamiltonians, for example, electron-photon coupling, where you can write down the Hamiltonian, but there's basically not a lot of expertise and not a lot of code available to solve these systems, because, yeah, I mean, what people have mostly done is, of course, molecules and materials, and whenever you introduce something non-standard into the Hamiltonian, then it's hard to take some numerical solution out of the box. Okay, so having said that, I'll briefly mention that also we can apply machine learning in order to learn coarse-grained molecular dynamics force fields. So now here, the ground truth is basically a molecular dynamics simulation that could be in an all-atom representation, right? And now we would like to learn an energy function of a coarse-grained force field that reproduces certain properties of the all-atom method. And one has to define basically what these properties are. So what is it that you want to maintain or restore in your coarse-grained simulation? Because of course you cannot have everything. If you remove degrees of freedom, there will be certain properties that you will lose. And the idea is that we basically want to keep the thermodynamics intact. So we define a mapping that goes from all atom to coarse-grained. So basically we define which are the particles we keep and which are the particles we throw away. For example, we throw away the solvent usually, and maybe we throw away some light atoms in the solute as well. And now we would like to maintain the thermodynamics of these remaining particles, which basically is equivalent to saying that the marginal, so if we take the equilibrium distribution, say the Boltzmann distribution in the canonical ensemble, and let's say we had that for the all-atom system. So then we can basically compute the marginal distribution on the coarse-grained system, which corresponds to a free energy that is generating this distribution, the free energy in the coarse-grained coordinates. And we would like to basically match these marginal densities. Or we would like to learn a free energy which gives rise to a probability density, which is just a coarse-grained density. So that's our goal. That's what I mean by restoring thermodynamics. And then, of course, that means if we compute other thermodynamic properties, such as the binding energy of two proteins or the protein and the ligand, which can be derived from this free energy landscape on the coarse-grained coordinates, then this should also be restored. And basically there is now, of course, dealing with free energies usually involves integrals that are not analytically solvable. But fortunately for this specific problem, there is again a variational formulation that allows us to train a machine learned model without having to solve the integrals. And the variational formulation has basically been devised by, I think I have it down here, that citation, by Will Noyd, who has used this formulation, especially in collaboration with Greg Wolf, on various handcrafted force fields to fit their parameters. And we are basically using this for machine learned force fields now. And the idea is that we can match forces. So you do your all atom MV simulation, you record the forces on the solute and or the forces on the coarse-grained coordinates, so the coordinates that you want to keep. And then you match them with the gradients. So the analytic force is computed from the coarse-grained energy function. Yeah, so you learn a coarse-grained energy function, compute its gradient or its negative gradient, which is the force generated by this coarse-grained force of this coarse-grained force field, and you're matching this on average with the instantaneous forces that you get from the atomistic simulation after projecting it to the coarse-grained coordinates. Now, of course, the atomistic, the forces in the atomistic simulation are random variables. So because there are other coordinates that we are throwing away, the instantaneous force on the coarse-grained coordinates will not be only a function of the coarse-grained coordinates, but also a function of the other coordinates, which means it's now a random variable in the coarse-grained coordinates. So we can only match this on average. So basically the average force is matched to the potential of mean force. That's the learning problem here. But we don't need to integrate. I mean, other than, of course, doing the MD simulation in the first place, which is hard enough. But maybe we can do this for a number of systems that are not too large, where we can achieve good sampling and then train our machine learning model on a representative set of systems. And so basically, this can be done for simple systems like alanine dipeptide, and we can basically generate a quite accurate potential of mean force And we can also do this for things like chignolin and show that chignolin can be folded in this coarse-grained force field. We can also use this trick in order to learn implicit solvent force fields by defining just keeping the solute coordinates as the post-graining operation, because then basically what we learn is the solvation free energy. And so currently what we are doing is to train these methods on a very large data set of thousands of different peptide simulations and small protein simulations. And basically the aim is here to learn a transferable protein force field, which is something that doesn't, the coarse-grained protein force field, which is something that doesn't really exist or only works with a lot of limitations. You know, things like Martini don't really resolve any conformational dynamics of the proteins, and other force fields such as awesome and I forgot the name of Jose Onochik's force field, SMOC. They are really designed for folding proteins, so they work well for if the protein is large enough and has a well-defined fold, etc. So the aim here is really to learn a coarse-grained force field that represents the thermodynamics of null atom force field. So there's a systematic coarse-grained procedure starting from a force field that we have enough trust in, and then learning something that is hopefully computationally more efficient. And so in the last part, I'd like to talk a little bit about the sampling problem. And so, of course, that's something that I've been working on, and my group has been working on for a long time. That kind of was one of the main obstacles in my PhD thesis, and people tend to kind of not forget the problems they've worked on their PhD thesis for some time at least. And so what you see here is molecular dynamics simulation, which has been patched actually together from many MD simulations according to a simulation on a Markov state model. This is a movie that has been generated by my friend and colleague John Codera. And you see in the middle how the protein is transitioning between different metastable or long-lived states, and on the sides how that corresponds to structure changes. And generally what we would want to compute is averages over such an ensemble, such as an equilibrium expectation value, which is basically a weighted average where the weights are given by the equilibrium density that is being sampled at a given thermodynamic condition. And this is very hard, unfortunately. And an example for that are these two little proteins, Barnase and Bar-star, where the energy function is known. So let's say we use an empirical energy function to simulate them, and we can do something like a microsecond simulation in a week. But unfortunately, a single binding process in this simulation box takes us on average a GPU year, and it would take us 1 million GPU years to observe a single dissociation event, which unfortunately is not the time that we have. So one approach to make progress there are these Markov state models, where basically the idea is to discretize state space and then don't use a single simulation, but start independent simulations from different starting points, and maybe also learn how to do that in an adaptive way. So try to avoid putting too much simulation in one spot and distributing that more efficiently. And so now I have to skip over things a little bit. And if we do that, we can actually solve this problem, this particular Barnase Bar-star binding unbinding problem, and identify a number of metastable states that are in between the dissociated and the fully bound state. So basically, we make use of the fact that there are some lower probability intermediate states that we can also start simulations from, and we can find them while we simulate, and then we can allocate a new simulation simulations to them, so that we start more efficiently than by always starting mostly in the bound state 99.9% of the time. So that's how we gain efficiency here. And then we can actually collect 2 milliseconds of total simulation data, which is a lot, but it's feasible, and get a full kinetic map of the binding unbinding dynamics, from which we can compute binding free energies and the binding mechanism and other things. So that is feasible, but it's still, of course, expensive, and the cost of this is comparable to what you need to launch a Saturn V rocket and deliver a payload to the moon. So one of the questions we've asked ourselves is, can we use machine learning, can we use deep learning, and especially generative learning, to make progress here? And so this led to the idea of Boltzmann generators. And the Boltzmann generator basically is a generative learning system which tries to sample the equilibrium density of molecular system more directly than by doing MD simulations or Monte Carlo simulations with tiny steps. And generative learning usually has the aim of learning and sampling a probability density. And in machine learning, this is usually defined by just having a database, for example, of images of VIPs or celebrities, as you see here. And then we try to train a neural network to learn what this probability density is and how to sample from it, so that we can generate new faces of fake celebrities. And that works quite well. And this is an old result that I'm showing because it's basically the first result obtained with a normalizing flow, which is the structure that we're using here. But now basically you can generate faces in super high resolution for the 4096 by 4096 that look extremely realistic and are indistinguishable for the human eye from photos of actual people. And so in physics, or in molecular physics, we have a slightly different setting. We're usually not given the data set that we want to learn the density from. I mean, this is exactly what we want to avoid doing here, because the sampling problem is hard. But instead, we're given the energy function, which defines the probability density that we want to sample. And there's a very interesting neural network architecture, which is called normalizing flow, that is suitable here. And the normalizing flow basically is an invertible neural network, which takes a probability density which takes samples from a probability density that we can easily sample from, this P of Z on top, something like a Gaussian density, and then transforms it into samples of the density that we want to have, P of X. And this allows us, because it's an invertible transformation, to use the transformation of random variables theorem and to compute the probability density of sampling an X at the output of the neural network. And if we know that, so basically we know the likelihood of the network generating something, we can match it to our target density, which we know point-wise. And so that's the idea here. We sample an easy to sample random variable at the input, put it through the neural network, generate candidates of the output, try to match the target density. And while we do that, we train the neural network to generate more realistic samples. And there will be a difference in the end. The network will never be perfect. And we fix the difference by using just statistical mechanics reweighting. So we use the neural network as a proposal step in a Monte Carlo framework, or we just do one-sided reweighting, so importance sampling, any of these options. And so basically, skipping over the implementation, what you can do is you can use these networks to combine that with other sampling methods to iteratively explore state spaces and then learn the Boltzmann generator to represent the highly populated states in these state spaces efficiently and to sample them efficiently, so that we don't have to wait for the rare events in sampling them. And we can push that up to systems like this. This is a small protein, VPTI, an implicit solvent, and we can generate structures like this in one shot. So we really sample 3000 dimensional Gaussian distributions here, transform through the network and generate all atom positions in one shot, and do that for different structures. And basically, we're currently working on trying to improve the neural network so that we can use this really for Monte Carlo simulations and then combine that with other sampling methods in order to get a more efficient sampling framework, basically. Okay, and with this, I'll skip over the last part and just, would like to thank my group and the organizations that have funded the research, and thank you for your attention.